Okay, let's just dive right in. From chatbots to image generators, the entire world of AI seems to have, well, completely exploded overnight. But what's the actual engine driving all of this? We're going to break down the revolutionary piece of tech behind today's most powerful AI. It's called the Transformer.
So to get started, here's a joke that wasn't written by a person. Nope, an AI generated that. And you know what? It might not win any comedy awards, but it perfectly sets the stage for our big question.
I mean, really, just stop and think about that for a second. It has to understand the whole setup punchline structure, the relationship between words like banana and mashed, and then put it all together in a way that makes sense. That's the mystery we're going to unravel today.
So how does this all actually work? Well, to get a handle on the AI of today, we first have to understand how it reads. And it's a completely different approach than, well, anything that came before it.
See, the old way, using these models called recurrent neural networks, or RNNs, was painfully slow. Imagine a computer reading a sentence one single word at a time, trying its best to remember what the first word was by the time it gets to the last one. It's like reading a book through a tiny peephole. Transformers, though, they see the entire sentence all at once. This lets them grasp the deep context and the relationships between all the words, all at the same time.
So how on earth does it see everything at once? Well, that brings us to the single biggest innovation that made all of this possible. It was introduced in a groundbreaking 2017 paper with a pretty great title, Attention is All You Need.
At the very heart of this breakthrough is something called the attention mechanism. It lets the model figure out how every single word in a sentence relates to every other word. It learns which words are most important to pay attention to in order to really understand the meaning of any other given word. It's what gives the AI such a powerful sense of context.
And this is why attention was such a massive leap forward. Not only could it suddenly grasp context over huge documents, but because it wasn't stuck reading word by word anymore, all the words could be processed at the same time, in parallel. This made training these massive models incredibly fast and scalable, which, yeah, is what really kicked off the AI boom we're all seeing today.
Okay, so let's peek under the hood for a minute. We're going to keep this conceptual, so don't worry, there's no heavy math here. But it's pretty fascinating to see the core logic at play.
You can really boil the whole process down to 3 stages. First, words get turned into numbers, or embeddings, that actually capture their meaning. Then, these numbers are processed through a series of transformer blocks, and that's where the whole attention thing happens. Finally, the processed numbers get converted back into a prediction for what the most likely next word should be.
So let's zoom in on that middle step, because that's where the real magic is. The core calculation is called self-attention, and there's a really great analogy that helps make sense of how it works. I want you to think of it like a web search, but happening inside the sentence. For each word, the model creates a query. That's the word asking for more context. Then it compares that query to all the keys, which are all the other words in the sentence. When it finds a really good match, it pulls the value, which is the relevant information, from that matching word. By doing this for every single word, it builds this rich, interconnected understanding of the whole text. Pretty cool, right?
But you know, this revolutionary design wasn't perfect right out of the box. As powerful as it was, it came with its own unique set of challenges that engineers had to get creative to solve.
The first major hurdle was just the sheer cost. I mean, because every single word had to be compared with every other word, the amount of computation required was just enormous.
So here's the problem. With the old models, if you doubled the length of a sentence, you pretty much just doubled the work. Simple enough. But with the transformer, if you double the sentence length, the amount of computation needed actually quadruples. It just explodes. Engineers have a name for this, quadratic complexity, and it made processing long text incredibly expensive.
So researchers developed some really clever workarounds. One of the most effective is called flash attention. It basically bundles a whole bunch of repetitive calculations into one single super efficient command. It's kind of like creating a macro in Excel that combines a dozen steps into one click. It just makes the whole thing way, way faster.
The next issue was focus. When the model was given a really long document, its attention could get kind of diluted. Imagine being asked to pick out the color blue from a palette that has 1,000 different shades of blue on it. With too many similar options, the task suddenly becomes much harder. So the fix was to make the model smarter about where it looks for information. New techniques were developed to sort of bias its attention. For example, making it focus more on recent words, or just using better pattern recognition to be more selective about what it pulls in.
And finally, there was this problem. Transformers are absolutely amazing at finding statistical patterns in language, but they're not naturally great at tasks that require multiple logical steps, like, say, solving a simple algebra problem.
The solution here was surprisingly simple, but really effective. It's called chain of thought prompting. Instead of just asking for the final answer, you actually show the model examples of how to break a problem down step by step. It basically teaches it to think through the problem logically, which dramatically improves its reasoning skills. It's like telling it to show its work.
So, with these challenges mostly solved, let's zoom back out and just take a look at the massive impact this single architecture has had on our world.
And it's so important to realize this isn't just about text anymore. The core ideas of the transformer have been adapted for a huge range of tasks, generating images and audio from a simple prompt, predicting complex protein structures, translating languages on the fly, writing code for programmers, and even mastering incredibly complex games like chess.
When it comes down to it, every single major AI model you hear about today, from OpenAI's GPT to Meta's Llama to Google's Gemini, is built on the foundation of the transformer architecture. It truly is the engine that's driving this entire moment in technology.
Which, of course, brings us to our final question. We've seen this one single architecture go from understanding language to generating art and solving major scientific problems. And that's all in just a few short years. It really makes you wonder, what will transformers learn to do next?